A computer with 128 gigabytes of memory sounds incredibly powerful. Put it next to a graphics card with only 24 gigabytes of VRAM, and the comparison seems almost unfair. One machine has more than 5 times the memory, so surely it should run large AI models faster, right? Not necessarily. In fact, when running the same model, that 24 gigabyte graphics card may respond several times faster than a computer with 128 gigabytes of ordinary system memory. In some situations, the difference can be so large that the smaller machine feels instant, while the larger one feels painfully slow. So what is going on? The problem is that we often compare memory only by capacity. We look at 128 gigabytes and 24 gigabytes as though they are simply two different size containers. But when you run a large language model, the size of the container is only part of the story. The speed at which the processor can read from that container may matter even more. Let me explain it with a simple analogy. Imagine that I have two warehouses. The first warehouse is enormous. It can store 128,000 boxes, but it has a narrow entrance, and workers can only move a limited number of boxes through the door every second. The second warehouse is much smaller. It can store only 24,000 boxes, but it is connected directly to a high-speed conveyor belt that can move boxes extremely quickly. If my job is simply to store as many boxes as possible, the larger warehouse wins. But if my job requires repeatedly pulling boxes out, checking them, and putting them back thousands of times every minute, the smaller warehouse may finish the work much faster. That is basically the difference between system RAM and dedicated video memory. System RAM is designed to serve the entire computer. The operating system uses it. Your browser uses it, your video editor uses it, the CPU uses it for almost everything. VRAM, on the other hand, sits directly beside the GPU and is built for moving enormous amounts of data into thousands of parallel computing cores. And large language model inference involves a huge amount of data movement. Every time the model generates a token, it needs to access a large portion of its weights. Those weights may contain billions of numbers. The model does not simply load those numbers once and then forget about memory. It repeatedly reads them as each new token passes through layer after layer. That is why large language model inference is often limited by memory bandwidth. Memory capacity determines whether the model fits. Memory bandwidth heavily influences how quickly the model can run once it fits. This distinction is extremely important. A computer with 128 gigabytes of RAM may be able to load a much larger model than a graphics card with 24 gigabytes of RAM. For example, a heavily quantized 70 billion parameter model may fit into 128 gigabytes of system memory without much trouble. But if the CPU has to read all those model weights through relatively slow system memory for every generated token, the model may produce only a few tokens per second. Technically, it works. Practically, you may spend a lot of time watching words appear one by one. Now take a smaller model that fits completely inside 24 gigabytes of VRAM. That model is sitting directly beside a massively parallel GPU. The GPU can read the weights through extremely high bandwidth memory and perform thousands of mathematical operations at the same time. The model is smaller, but the entire pipeline is much faster. This is why a 24 gigabyte GPU can sometimes embarrass a computer with 128 gigabytes of RAM. The GPU is not winning because 24 is somehow larger than 128. It is winning because the model fits inside the GPU's fast working area, and the GPU can process it without constantly waiting for data. There is another issue people often overlook, where the computation happens. When a model is stored in normal system memory, it will usually be processed mainly by the CPU unless some of its layers are transferred to a GPU. Modern CPUs are powerful, but they have a relatively small number of complex cores. They are excellent at running operating systems, applications, game logic, and tasks that require low latency or complicated decision-making. GPUs are built differently. Instead of a small number of powerful cores, a GPU contains a very large number of simpler computing units. Large language models rely heavily on matrix multiplication, which is exactly the kind of workload GPUs are designed to perform in parallel. So the graphics card has two major advantages at the same time. It has faster access to its memory, and it has hardware that is better suited to the calculations used by the model. This is why comparing RAM and VRAM only by their gigabyte numbers can be misleading. It is a little like comparing a passenger bus with a race car. The bus can carry far more people, but if the goal is to get one person around a racetrack as quickly as possible, the extra seats do not help. Of course, there is an obvious limitation to the 24 gigabyte graphics card. The model has to fit. Once the model becomes larger than the available RAM, things become more complicated. One solution is quantization. Instead of storing every model weight using 16 bits, we may reduce it to 8 bits, 6 bits, or 4 bits. This can dramatically reduce memory usage. A model that would originally require around 40 gigabytes might be reduced enough to fit inside 24 gigabytes of RAM. But quantization is not magic. Depending on the model and the quantization method, it can slightly reduce output quality. It may also affect reasoning, accuracy, or performance on difficult tasks. Some models handle aggressive quantization surprisingly well, while others become noticeably less reliable, and even after quantization, some models are simply too large. When that happens, we can use GPU offloading. Part of the model is placed in VRAM, while the remaining layers stay in system RAM. The GPU processes the layers it can hold, and the CPU or system memory handles the rest. This allows a 24 gigabyte GPU to run models that require more than 24 gigabytes of memory. But now we introduce a new problem. Data may have to move between system memory and the graphics card through PCI Express. PCI Express is fast by normal computer standards, but it is much slower than the bandwidth available inside the graphics card itself. So every time data has to travel between RAM and VRAM, the GPU may be forced to wait. A powerful GPU that spends its time waiting for data is like a professional chef standing in a kitchen while the ingredients arrive one item at a time from a warehouse across town. The chef is fast, the delivery system is not. This is why performance can drop sharply when a model no longer fits completely inside VRAM. The difference between fitting and almost fitting can be enormous. A model using 23 gigabytes of VRAM may run beautifully on a 24 gigabyte graphics card. A model using 27 gigabytes may require some layers to be offloaded, and suddenly the speed falls much more than you might expect from a difference of only 4 gigabytes. There is also more than just the model weight itself. The computer needs memory for the runtime, temporary calculations, and something called the KV cache. The KV cache stores information about the tokens the model has already processed. It helps the model avoid recalculating the entire conversation every time it generates a new token. As the conversation becomes longer, the KV cache grows. That means a model that fits comfortably with a short prompt may run out of VRAM when you give it a very long document or use a large context window. This is why specifications such as "this model needs 20 gigabytes" should never be treated as an absolute number. 20 gigabytes may describe only the model weights. You still need extra room for the context, the software, and the operating environment. So does this mean 128 gigabytes of RAM is useless for AI? Absolutely not. Capacity is still extremely valuable. A computer with 128 gigabytes of RAM can load models that a 24 gigabyte graphics card cannot load by itself. It gives you more flexibility to experiment with 70 billion parameter models, mixture of experts models, long context windows, and multiple AI applications. It can also allow you to offload more layers instead of relying on storage. And system RAM is still much faster than using an SSD as emergency memory. The 128 gigabyte E-machine may be slower, but it can complete workloads that the 24 gigabyte GPU cannot even start without quantization or offloading. So the real question is not, which number is bigger? The real question is, what do I want the computer to do? If I want to run a smaller model extremely quickly, a strong GPU with 24 gigabytes of fast RAM may be the better choice. If I want to experiment with much larger models and I am willing to accept slower generation, 128 gigabytes of system memory gives me more room. If I want both large capacity and high speed, then I need a more expensive solution: multiple GPUs, a professional GPU with more VRAM, a high bandwidth unified memory system, or a dedicated AI workstation. And this is also why unified memory computers are so interesting. Unified memory is not exactly the same as ordinary desktop RAM. The CPU and GPU can access the same memory pool without copying everything back and forth between separate RAM and VRAM. That can make it possible for the GPU to work with models far larger than the VRAM available on a typical consumer graphics card. But even unified memory does not automatically defeat a powerful dedicated GPU. You still have to consider memory bandwidth, GPU computing power, software optimization, power limits, and the specific model being used. A machine may have 128 gigabytes of unified memory and run a huge model locally, but a desktop graphics card may still generate tokens faster when the model fits inside its 24 gigabytes of VRAM. That is the part people often miss. Being able to run a model and being able to run it quickly are two completely different achievements. Large memory gives you access. Fast memory and strong compute give you speed. And sometimes, the smaller but faster memory pool wins. So the next time you see a computer advertised with 64, 128, or even 256 gigabytes of memory for artificial intelligence, do not look only at the capacity. Ask how much memory bandwidth it has. Ask which processor can access that memory. Ask whether the model will run on the CPU, the GPU, or both. Ask whether the complete model can stay inside the fastest memory pool, because in local AI, the largest number on the specification sheet is not always the number that determines the experience. A 128 gigabit e-computer may be able to hold a much bigger brain, but if that brain can only read its own memories through a narrow doorway, a 24 gigabyte graphics card may still answer first.